Hello students, welcome to today's video. In this video we are going to discuss about the electric field intensity on the equatorial line of an electric dipole. So earlier we have discussed what is an electric dipole. The electric dipole is a system of charges it consists of two charges, minus q and plus q, two opposite charges separated by a small distance. Here we have taken the distance as from here to here up to the midpoint, it is a, and from this midpoint to this charge the distance is a. So as a result we get the total distance from minus q to plus q charge to be twice a. Now if we draw a line here passing to the midpoint which is perpendicular to the dipole, then this line is an equatorial line of the dipole. So in this lecture we have to discuss about the electric field intensity at any point on this line. Here we have considered a point P which is at a distance r from the midpoint O, which is at a distance r from the dipole. We have to calculate the electric field intensity at this point. Now the electric field intensity can be calculated in two ways. First, at this point we will get an electric field intensity due to the minus q charge at the point A, and similarly we'll get another electric field intensity value for this charge at this point. Since if we place a positive charge, unit positive charge at this point, which is which I have written as 1 coulomb, then at this point this charge will experience a force due to this charge as well as this charge. So what we will get two values of electric field intensity at this point. So at this point what we can see is there is a positive charge here while there is a negative charge here. So this negative charge will try to attract this positive charge. As a result we will get a force along this direction, and we will also get a value of electric field intensity at this point. This electric field intensity will be along this direction, since we know that the direction of electric field intensity is same as that of the direction of force in which the force acts on this charge. Similarly, here we have a positive charge as well as here there is a unit positive charge. So what will happen? This positive charge will try to repel this positive charge, this unit positive charge. As a result, this positive charge would experience a force in this direction along this direction. So what we will get? We will get an electric field intensity value here due to this charge, and that charge will try to repel this charge. So as a result we will get an electric field intensity in this direction, or the direction of electric field will be along this direction at this point. So what we have got is there are two directions of electric field intensity. First, due to charge q1 minus q, we have put the electric field intensity direction as E1. We have shown it as E1 along this direction. For the charge plus q at the point B, the direction of electric field intensity at this point is shown as E2, which is along this direction. Now we have got two vectors here, one is E1 and the second vector is E2. Both electric field intensities or electric fields are vector quantities. So we have got two vectors here. Now we have already read about vectors in the previous class, in class 11. So what we can do here is we can resolve these two vectors into a resultant vector. Now resolving these two vectors or finding the resultant of these two vectors, we will get a vector along this direction. Here we can see that we have taken this angle to be theta as well as this angle to be theta. If these two angles are theta, then this angle will also become theta, whereas this angle will also become theta. So as a result, what is the angle between these two vectors? It is twice theta. See, if we resolve this E2 into cos and sine components, then what we will have? We will have a cos component along this direction which will be E2 cos theta, and along this direction we will get another component which is E2 sin theta. Similarly, for this electric field E1, we will get two components. We can resolve it into two components. One is E1 cos theta along this direction, and another component which is a vertical component along this direction, that will be E1 sin theta. Since since we will come to know that the electric field, that is E1 and E2, are equal in magnitude. As a result, we will get the electric field which is along this direction, and electric field component which is along this direction, and electric field component which is along this direction to be the same, but they are in the opposite directions. So as a result, these two components will cancel out each other's effect. There will be no net electric field at this point due to the vertical components. There will only be the horizontal components, where along this direction the electric field intensity component or electric field component due to this electric field and the electric field component of this electric field will add up vectorially along this direction. So as a result, we'll get a net electric field at this point. Our main objective is to find out the electric field intensity in this point, which we can see to be along this direction. So we have to prove it mathematically now. So we have written here, let a unit positive charge be placed at a point P at a distance small r from O. We have considered a point P which is at a distance small r from O. Now the magnitude of electric field at P due to the charge minus Q at A is. So what we'll have to calculate first, the electric field due to the minus Q charge. Secondly, we will have to calculate the electric field due to the charge plus Q which is at a point B. So here we find the electric field at point P due to the charge minus Q at A. That will be equal to, you already know the formula, that E equal to KQ divided by the distance square. What we have put here is K means it is the constant 1 by 4 pi epsilon naught. You can put the value here, or at last you can put the values, it will be the same thing. So we have just simplified it, therefore we have written K, and E1 will be equal to KQ divided by, here the charge is charge was minus Q actually, but what we have taken here is only the magnitude of the electric field. So for the magnitude of the electric field, we can simply consider the magnitude of the charge, not the sign. Okay, so what we have taken here is only Q, not minus Q. Here the distance between the points P and the point A is AP. From here to here the distance is AP, so we have put in the denominator AP square. Now if you use Pythagoras theorem, what was the formula for Pythagoras theorem? It was hypotenuse square is equal to base square plus altitude square. The hypotenuse here we can find in this triangle to be AP. So AP square will become equal to, what is the base here? From here to here the distance is small a, so the base will become A square, and the base will become A. So here we can write A square plus the distance, which is the altitude. This distance is smaller, so we can write here in place of altitude smaller, and it will be altitude square, so we have written here R square. So what we will get, AP will become R square plus A square to the power 1 by 2. In place of AP, we can write here, in place of AP square, what we have found here is A square plus R square. So we have written here R square plus A square. Now what will be the direction of E1? The direction of E1 is along this direction, since this charge is attracted by the negative charge minus Q. So we will get an electric field along this direction. So it is along P to A. So we have written here along PA. Similarly, we can also find the magnitude of the electric field at P due to the charge plus Q, which is at a point B. So we have calculated the electric field intensity at a point P due to the charge plus Q at the point B as E2, which will be equal to KQ divided by the distance square. What will be the distance? It will be similar here, so we can write R square plus A square. Now what we have seen is the magnitude of E1 and E2 is same. So we have written here E1 is equal to E2. We have written this in terms of magnitude. Now what we have got, according to the diagram that we have shown, what we have got is a vector along this direction, that is the direction of E1, and a vector along this direction, which is the direction of E2. For these two vectors, they will add up vectorially, so we will get a resultant vector along this direction, which I have shown as E. First of all, we can resolve this E2 into two components. One is the cos component, which we can write as E2 cos theta if this is the angle theta, and a vertical component which will be E2 sin theta. Similarly, for the E1 vector, we can resolve it into two components. One is E1 cos theta along this direction, and the other is E1 sin theta along this direction. Now what will happen, the magnitudes of E1 and E2 is same, so the value of E1 sin theta will also be equal to E2 sin theta, since these two angles are the same. So what will happen, this electric field component and this electric field component will cancel out each other since they are in the opposite direction. So what we will get? We will get a resultant vector along this direction, which is the addition of the E2 cos theta component and the E1 sin theta component, E1 cos theta component, sorry. We'll have to calculate the net electric field along this direction. Then we can calculate the net electric field using the vector addition law. So here we can write E equal to root over. How do you already know how we find the resultant of two vectors. We can, if here there is a vector A along this direction and another vector B along this direction, and if theta is the angle between them, then we can write the resultant vector. We can take it as C. So the resultant vector will become root over a square plus b square plus twice ab cos theta. You have already studied about these vector addition rules in class 11. So we need not discuss those once again here. We will just use a formula here. In this case, what is the angle? Theta plus theta, that will be equal to twice theta. So the net electric field at the point P is E equal to root over E1 square plus E2 square plus twice E1 E2 cos, what will be the angle? Twice theta. If we solve this, then we will get here E1. We have already found that E1 is equal to E2. So we can write here, we can replace E2 in place of, we can replace E1 in place of E2. So here we can write that this will become E1 square plus E1 square. So this will become twice E1 square plus 2 E1 E2. So here we have put E2 is equal to E1. So this will become E1 square. I have written here 2 E1 square cos twice theta. Here also there is a term 2 E1 square, and here also there is a term twice E1 square, which is common to both the terms. So we can take it out. We can write it outside the bracket. The square root will be there, and inside the square root we can take 2 E1 square as common, and inside the bracket there will be 1 plus cos twice theta. Now you know that the value of 1 plus cos twice theta is equal to 2 cos square theta. So we have written here in place of 1 plus cos twice theta 2 cos square theta. Now if we take the root, then what will be the value of electric field? It will be twice E1 cos theta. So we have got the value of the total electric field E to be twice E1 cos theta. Now there is an important point you must remember, that the direction of, in this figure, the direction of the dipole moment, that is P, is conventionally taken along the negative charge to the positive charge. For a dipole, always remember that conventionally the direction of dipole moment is always taken from the negative charge towards the positive charge. So we have denoted the dipole moment of this dipole as P, which is along this direction from minus Q to plus Q. Now what we have seen here is the direction of E and the direction of P is opposite, or we can say that the direction of E, total electric field E, is opposite to the direction of P. So we have written here, since the total electric field is opposite to P, therefore E can be now written as, in terms of P we are writing this in terms of a unit vector P. So we have to take the negative sign, since the direction of E and direction of P is opposite. Therefore we have taken the negative sign here. The remaining part will be same, twice E1 cos theta. So I have written here twice E1 cos theta. Now this since we are writing this in terms of P, which is the dipole moment, or so we have written here a unit vector for P. We have written here P cap. Now we can simply put the value of E1. What was the value of E1? We have found it to be KQ divided by R square plus A square. So in this equation we are just replacing the value of E1. It will be Q divided by R square plus A square. What will be the value of cos theta? So simply in triangle AOP, we take the triangle AOP. In this triangle, the value of cos theta will be the base by hypotenuse. What was the base? It was A, and what was the value of hypotenuse? It was R square plus A square to the power half, or we can say that it is A by root over R square plus A square. So simply also replace the value of cos theta. Putting this value in place of cos theta, we get this term, A by R square plus A square to the power half. and there will be the unit vector p. So if you combine r square plus a square here to the power 1 and r square plus a square to the power half, we get r square plus a square to the power 3 by 2. The remaining part is the same, it is minus 2 k q a. Now if we put the value of k, which is the constant, this will become 1 by 4 pi epsilon naught. In place of k, we'll have to replace 1 by 4 pi epsilon naught. So I have written here 1 by 4 pi epsilon naught into, this term will remain the same, minus 2 qa divided by r square plus a square to the power 3 by 2. The unit vector will be there, p, along, which is the unit vector along the direction of dipole moment p. This formula what we have got now is a very important formula, and this is the electric field intensity on the axial line of an electric dipole. This is a very important formula, please keep it in mind. If we will have to study a special case now, if the point P is at a very large distance from the dipole, that is if and the distance is large, r is much less than a, if r is much greater than a, then we can neglect the term a from the denominator of this equation. So what this equation will now become, if r is much greater than a, then e will be minus 2 qa, that will be minus 2 qa divided by 4 pi epsilon naught. So 4 pi epsilon naught, here the power of r will become to the power 3. Why? Because here we have neglected the term a square, have neglected the value of a compared to r, since a is much smaller than r. So in this equation, the power of r becomes r to the power 2 into 3 by 2. 2 and 2 cancel out, so r will become the power of r will become 3. Here we have written r to the power 3. The dipole, the unit vector will be there. In the next step, we have already known that the value of dipole moment, that is p, is equal to q into twice a. Here q is the magnitude of any of the charge and twice a is the length of the dipole or the distance between the charges. So what we have in the numerator here, twice qa, or we can write this as q into twice a. If this is the value of q into twice a, then we can substitute this value as dipole moment p, which is a vector. So we have just replaced the value of 2 into q into twice a as dipole moment p. This is the electric field intensity on the axial line of an electric dipole if the point is very far away from the dipole, or if the point is at a very far distance compared to the length of the dipole. Is it clear? So now what we can conclude, we have already studied two cases, that is the electric field intensity on the axial line of an electric dipole and the electric field intensity on the equatorial line of an electric dipole. So what we have found out is the electric field intensity on the axial line is equal to, and we have written here E axial, that is equal to 2p divided by 4 pi epsilon naught r cube. We have considered the special case here if r is much greater than a, that is the distance of the point from the dipole is much greater than the point, the distance of between the charges. We have got the value of electric field on the axial line to be this much, and on the equatorial plane at a point for the electric dipole, we get the electric field intensity as minus p divided by 4 pi epsilon naught r cube. Simply neglect the negative sign, we can take only the magnitude. If we consider only the magnitude, then what we can see is E axial becomes 2 times of the equatorial, or we can say that electric field intensity on the axial line of an electric dipole is twice that of the electric field intensity on the equatorial line of an electric dipole. Is it clear? Thank you.